Basic quantities that involve magnitudes such as 45 pounds or 60 miles per hour can be represented by real numbers, technically that are called scalars. Okay, so all of those things are technically just scalar terms. Pretty much for your entire existence, you've only worked with scalar terms. Other quantities, called vector quantities, involve both things called magnitude and direction. So we're going to have a magnitude and we're going to have a direction. Typical vector quantities include velocity, acceleration, force. So those of you in physics, you have worked with the idea of vectors. I just don't think we have used vector mathematics to explain them as well as you will see here, because we're really diving into the math of these forces. So for example, if you have the scalar of 50 miles per hour, but you add a direction, east, 50 miles per hour east is a vector quantity because it told me the magnitude, 50, and the direction, east. That is a vector quantity. A vector quantity can be represented with a directed line segment. So in geometry, we would have called these like a ray, but we don't have like a point at the end here and off to one side. It's called a vector, a segment that is directed. This is our vector quantity. Let's highlight that word for us. The length of the vector represents the magnitude of the vector quantity. The direction or angle of the vector indicated by the arrowhead indicates the direction of the vector. So if we see this vector right here is a 10-pound vector 30 degrees above the horizontal. So it gave me the magnitude, the length essentially, 10, and the direction, 30 degrees above the horizontal. So remember, we've done some trigonometry with these concepts. When we did angles of elevation and depression, or all of the navigation we've done in this course, those were mathematical trigonometric functions, but now we're going to put them into vector quantities, which is how most science, and advanced math is done. When we write vectors, we either use boldface type, which is really for a computer, or arrows over the letters, so it will either look like this, bold. I think your homework does this. But our handwriting is not that easy to do that, so we're going to put an arrow above the two letters to represent the vector shown in the figure. When the two letters name a vector, the first letter indicates the initial point, and the second letter indicates the terminal direction or terminal point. Knowing these points gives us the direction of the vector. So if you see the two vectors I have here, vector U or vector capital A, they're different vectors because vector U goes from O to P. It would be called vector OP. And vector A goes from P to O. That's a completely different vector. So the direction it's going is very important for you when you're looking at vectors. They have the same magnitude, but they technically go in opposite directions since the letters are written backwards. The magnitude, to discuss the magnitude of a vector quantity, so if I'm saying OP with the little line over it, I'm talking about the entire vector. But if I want to just talk about the magnitude, or you can think of it as length of the vector, you write it with the absolute value bars. And then I personally will be writing it differently than this. I think this is a typo I never fixed because I can't figure out that symbol. You'll put a little arrow above OP, even when it's inside those absolute value bars, because it's the magnitude, absolute value, magnitude of vector OP. A computer can type boldface. Our handwriting doesn't really have like boldface, so we put the arrow on top of it to indicate that it's a vector. Two vectors are equal if and only if they have the same direction and the same magnitude. So if you see the ones down here, we have a whole bunch of examples. A and B are equal because they're the same length, magnitude, and they go the same direction. C and D are also equal to each other because they go the same direction and they're the same length or the same magnitude. But if we were comparing C to E, do those go the same direction? Are you sure? One looks like steeper than the other, right? So do they go the same direction? So they're not equal vectors. This one is going the same direction as A and B, but is it the same magnitude? No, so it's also not equal to anything else on this page. So they have to be equal in magnitude, and they have to be equal in direction to be equal vectors. Okay, there's a lot of info in this lesson because, again, this is the first time we've seen vector quantities. Got to get a lot of vocabulary out there. Including what it means to do the sum of a vector. When we're working with the sum of two vectors, we are also creating a vector. So the sum of two vectors is a vector. There are two ways to find the sum of the vectors A and B geometrically, which is how we're going to do them, aka we're drawing pictures. You're going to place the initial point of vector B at the terminal point of vector A. So just to make sure we see what's happening here. If I was using vector B, that's this guy. I put the initial point of vector B at the ending or terminal point of vector A. So we have vector A, and wherever A ends, we put B right after it. So the initial and terminal points have to connect. It's purple. The vector with the same initial point as A and terminal point as B is the vector sum A plus B. And to tie this back to why this goes here, just a little preview, what have I created in this image? A triangle. We just learned a bunch of laws of triangles. So vectors, when we add them together, create triangles. We go back to the law of triangles that we just learned. The other way we could do this is to use what's called the parallelogram rule. Ooh, that parallelogram rule wrote that word way too big. Let me try that again. There we go, fit this time. You're going to place vectors A and B. So let's make sure we remember what we're looking for here. So vector A is the purple guy. Vector B is the green guy. And we're going to place them to where their initial points are at the same place. Do you see how I've just basically taken this vector B and like scooted it over so that they both start at the same place? If you look on the outsides and we connected the dots, this would make a parallelogram. Therefore, if you think about it geometrically this way, the diagonal of the parallelogram is this same vector that we had up here making the triangle. So you can think of this either as what I'm calling the triangle method or the parallelogram method. Either way, that's how you do the sum of two vectors. Parallelograms can be used to show that vector B plus A is the same as vector A plus B because vector addition is commutative. You're going to get a new vocabulary word here. The vector sum A plus B is the resultant of vectors A and B. So we're talking about the resultant as what we get when we add these two things together. So the sum is called the resultant. You can think of it like the result when we add them together. I know that I'm talking about the parallelogram rule, and there's a whole lot of things that come with parallelograms that you either slept through or forgot from geometry class. So let's go over them. In a parallelogram, it's called parallelogram because the opposite sides are parallel. So if I was drawing this on here, the parallel symbols are the little arrows. So these two are parallel to each other. And the top and bottom are parallel to each other. That's a rule for parallelograms. We also know that in a parallelogram, opposite sides and opposite angles of a parallelogram are equal. So that means for us, that the sides of here are the same, put the tick marks, and the top and bottom are the same length, put the tick marks. We're also told that the opposite angles, so like this little angle and this little angle, and then the obtuse angle and the obtuse angle on opposite sides of that parallelogram should be the same number. It also says that adjacent angles of a parallelogram are supplementary. Ooh, supplementary. What does that mean they add up to? 180. So this guy should be added together to make 180 with that guy, which then means this guy and this guy add together to make 180. They're adjacent to each other or touching. That works all the way around the parallelogram, by the way. The last thing we know from parallelograms that maybe is not as helpful to us is that the diagonals of a parallelogram bisect each other, but they don't necessarily bisect the angles of the parallelogram. So what that means is that if we have, I'm going to zoom in. Oh, maybe I'm not going to zoom in. There we go. If I have diagonals going from one corner to the other corner on one side, and one corner to the other corner on the other two corners, that those diagonal lines bisect each other. They mean cut it perfectly into two. So like this piece and this piece are the same, and this piece and this piece are the same. Knowing the property of the shapes from geometry class allows us to use a lot of these properties with our parallelogram rule for vectors to answer lots of questions. We have a few more definitions and concepts before we get into a practice problem because, again, vectors are new to us. But going back to vectors and leaving geometry for a second, for every vector, there is a vector, negative v, that has the same magnitude but an opposite direction. So do you see how these go one direction, same length but the opposite direction? Those are called opposite vectors. Acceptable? What's nice, though, is that we have one more vector that's special called a zero vector. The sum of positive and negative vector v have a magnitude of 0, because if we add them together like a positive number and a negative number, they cancel each other out, become 0, right? That same thing happens with vectors, so it's called the zero vector. All of these properties of vectors allow us to use them like they're regular numbers, which is what we need to be able to use our law of sines. The last thing here is that the product of a real number or scalar, some number k, and a vector u is the vector k times u, and has a magnitude of k times the magnitude of u. That is basically telling you that if you take a vector quantity and you double it, the magnitude will double. If you take a vector quantity and you take a half of it, the magnitude will become half of it. So if you see here, this is u. This is 2u. You see how it's doubled? This is 1.5u. See how it's 1.5 times? This is half of u. This is half the size. Did any of those directions change? No, because we multiplied by a scalar number. But when we multiplied by -2, not only did it double in size, what did it do? Flip side. It's now the opposite vector. Notice the arrow came down. That tells us that scalar numbers, the way they've always worked, times 2, times 5, times -3, with regular quantities, also work for vectors. All of this put together will allow us to answer physics questions and speed and velocity questions using the properties of triangles, because those kinds of things have a direction as well as a magnitude. Example 1, we're going to find the magnitude of a resultant. Remember, a resultant is what you get when you add two things together. It says two forces of 15 and 22 newtons act on a point in the plane. Note that a newton is a unit of force that equals 0.225 pounds. If the angle between the forces is 100 degrees, find the magnitude of the resultant force. Okay, first things first, just like with our laws of triangles, we got to draw a picture. So here's my point that's being acted on. Boom. That is my initial point for both vectors. It says that we have two forces. One of the forces is going to be 15 newtons. So here's my 15 Newton force. Pow. 15 newtons. Actually, I didn't want to write that there. I want to call this vector A. At the same time, a 22 newtons force also acts on the plane at an angle of 100 degrees away from the other one. So then it's going to look something like this. Here's vector B. That's 22 newtons. Oops. The angle between them is 100 degrees. I want to know the magnitude of the resultant force. The resultant force, if we use the parallelogram rule, is going to be very easy to find. Okay, wait, I guess, do we understand how I drew this picture? There's a single point where we have two forces acting at the same time. Pow and pow. Like as if you're playing pool, right? And two balls hit a point at once. It has two forces acting on it. We have to figure out where that ball is going.
Wait, but isn't it if it's acting on it, it's going towards it?
As if this is the point and the force is going pow.
Yeah.
And the force is going pow at the same time. So where is this point going if we have some force going that way and some force going that way? Like diagonal, right? That is the resultant vector. We get this by using that parallelogram rule and making a parallelogram out of these two forces. My resultant vector is going to be the vector that I get going the exact direction you pointed with your fingers. This resultant force is the force A plus vector B. Let's back up again. Do we understand the picture now? Better? So we have this parallelogram. Our job is to figure out the magnitude of the resultant force. So our job is technically to find the magnitude of vector A plus vector B. We want to know the length of, for lack of a better word, vector A and vector B. We have this information. We know that vector B is 22 newtons. We also know that vector A is 15 newtons. So question, using the properties of triangles, can I just focus on this part of the triangle? The answer is yes, because if this is 15 and it makes a parallelogram, how much is this? 15. Let's put that 15 down there so it looks right. Using the geometric rules of parallelograms, this angle, like both sides of it, not the cutout side, but this angle and this angle have to add to what? So what is this angle? 80 degrees. If we are looking for this length, this magnitude, you are given side, angle, side. What did we use last class to solve a side, angle, side situation? Law of cosines. The law of cosines, I'm going to write it in regular letters, says that a squared should be equal to b squared plus c squared minus 2bc times the cosine of not b big A. If we rewrite this in terms of what we have on this image, we can use the vector quantities inside the law of cosines to solve for that resultant vector. We would say that the magnitude of A and B squared would be equal to the vector quantity A squared plus the vector quantity B squared minus 2 times the vector quantity A times the vector quantity B times the cosine of what angle? Don't give me a letter, give me a number. What's the included angle here? The included angle? 80. Now to make this more scientifically correct, every single one of these, since we're dealing with magnitudes, needs to have the absolute value bars. Okay. This is, again, literally just the law of cosines, but using the letters from the vector. Do you see how it's the same as this? The angle across from, or the side across from the angle I know, the length of it, so magnitude, is equal to the length of the two sides squared minus 2 times the two sides times the cosine of 80 degrees. Let's fill in what we know here. If we are finding the vector quantity, or the magnitude of the vector a plus b, the resultant, it would be the square root of, what is the magnitude of a? So what is the length of vector a? 15. We're going to square that. Plus the magnitude of vector b, 22. We're going to square that. Minus 2 times those two quantities again, times the cosine of 80 degrees.
Wait, where did the 22 come from?
Where did the, which one?
The 22 of it? Oh.
Oh, that is just, let me go ahead and move it though, because you're right, that is kind of confusing. How about I do this? Is that better? Yeah. I can do this number. Okay. Okay. That's a calculator question. Square root, put all that in there, which we did before. I'm going to fast forward. The magnitude or length of vector a plus b, the resultant vector, is 24.3802 newtons. So you can think of magnitude as length. If we're putting these forces on a piece of paper and describing them as sides of a triangle, it's like the lengths of the triangles, the sides. All of the laws we used before this come along. We also have a method that will find what it is necessary to counterbalance the resultant. That is called the equilibriant. So the equilibriant, I spelled that wrong. Let me try again. Equilibriant. The equilibriant is the vector that is opposite from the resultant vector. And remember, opposite vectors are just positive and negative versions of themselves. So the vector u has an equilibriant that is vector negative u. This is very helpful, especially in physics, if you're trying to combat the forces, like let's say we've put something tilted on a piece, a tilted table, and we want it to stay there. We have to know the friction required to keep it there as the resultant or the equilibriant of that motion, of the forces. Okay. In example 2, we're going to find the magnitude of the equilibriant and then eventually find the angle between the equilibriant and one of the forces. But let's just stay focused first on what we are looking for. First, we're going to find the magnitude of the equilibriant. We have to draw a picture because we have to know what we're dealing with here. So it says there are two forces of 48 newtons and 60 newtons acting on a point A if the angle between the forces is 50 degrees. Okay, let's see if we can do this one. What is the first force? 48. And I'm going to draw it going a particular way this time because I know what's coming. Let's have that 48 be acting on the point and go this direction. So we're going to call this one, we'll just put 48 right here, the vector worth 48. There is another force. What's the other force? 60. So 60 newtons is also acting on it at the same time, but it's going to go like this way. It says the angle between the forces is how much? 50 degrees. We're going to find not necessarily the magnitude of the resultant. We're going to find the magnitude of the equilibriant, which means we need two things. We do need that resultant vector, but more so, we need the magnitude of the opposite vector from that one. But what's nice is that since they are equilibriants, the magnitudes are going to be the same. The direction's going to be opposite, but the magnitude would be the same. Last time, once we had our picture drawn, what did we do to like make a cute triangle for ourselves? The parallelogram rule. So I'm going to close this up with a parallelogram. Your parallelogram doesn't have to be perfect because like this is so not perfect. That's more of a kite actually, but pretend it's a parallelogram. Pretend I'm good at drawing. Okay, we're going to call this point A. We'll call this corner B and we'll call this corner C just because I can see what's going to come here. If that blue part is 48 newtons, then from B to C, because this is a parallelogram, will also be 60 newtons. Again, ignore the fact that this doesn't quite look like a parallelogram. It's not my best. The other thing we know, once we know it's a parallelogram, is that if this corner is 50, what's this corner? How did you get that? Correct. These angles, adjacent angles, are supplementary. So that means this one up here is 130 degrees. Do you see again how we have created a triangle from here to here to here? That is side, angle, side. We can use the law of cosines. Drawing the picture is tough, but it is step one in all of these. If you've taken physics before, I'm assuming that was always step one in the forces unit, so you could see where it was going. So if we write this down, here, let's label some more stuff. We're going to call this vector V, so that this is the negative V, so that we know what we're searching for. The law of cosine says that the opposite side's magnitude squared would be equal to the two side lengths squared, so this is going to be AB squared, plus BC squared, minus 2 times the vector magnitude for AB times the vector magnitude for BC times the cosine of the angle between them. What is that angle between them?
Wait, what was the question?
What is the angle I should put right here? 130, because this is one side and this is the other. We want the angle between them. If you wanted to use letters, you could call that angle B since we named it B, or angle ABC since we gave 3 things 3 letters. Once we have this point, we're just throwing things into this formula. The magnitude of V, which would be the same as the magnitude of the resultant, will be the square root of the magnitude of AB, which is 48, plus the magnitude of BC, which is 60, minus 2 times the magnitude of AB times the magnitude of BC times the cosine of 130 degrees. We throw that all in a calculator, we make sure it's in degree mode, and we find that the magnitude of vector V, that resultant vector, would be 98.0125 newtons. But remember, that's this vector. We were asked for the magnitude of the equilibriant, which is the opposite. What is the magnitude of the opposite if the resultant is this much? It would be like the same. So the magnitude of the equilibriant, aka the opposite, would literally be the same because the magnitude is the same. The only thing that changes is the directions. And next class we'll figure out the direction of this angle.